Sorry, you're going to hear me repeat myself now. I'm going to say something like this, Brian. Work is a scalar. It has no direction. However, it can be negative or positive. If the force is in the same direction as motion, like F1 in this little picture here, we say it's doing positive work. What we're really saying, Hannah, is it's adding energy to the system. If you have a force that's in the opposite direction of the motion, like F2 in this picture, we say it's doing negative work. It's bleeding energy off. So coal, although work can be positive or negative, it's not a vector. It has no direction, much like your future, right? So what does negative work mean? We got to talk about energy. Energy is defined as the ability to do work. How is work defined? Force times distance. So I guess, Sierra, we're saying if an object has energy, it has the ability to exert a force over a distance. There are many types of energy. There's the energy of motion. All moving objects have energy because if they hit you, they will exert a force over a distance. We call this type of energy kinetic. Heat is a form of energy, Brian. Heat is typically caused by friction. There's gravitational potential energy. This is stored by an object's height. The higher you lift an object, the more energy you're giving it. Chemical potential energy, for example, in gunpowder or in the food that you eat. Nuclear energy, elastic energy. When I stretch something, I'm doing force times distance. I've done work on this object. I have added energy to the system. How do I know? If I shot this at Brian, when it hit him, it would apply force over a distance. It has energy. Oh, and it would be moving in the middle, so it has kinetic energy as well. Sound is a form of energy. Nuclear energy, that which is stored within the nucleus. In this course, though, we're going to look at mechanical energy, which is broken down into two main types: kinetic and potential. Potential is stored energy. Kinetic is moving energy. If an object is at rest, what do you think its kinetic energy would be? Zero. Okay. This explains negative work. Then, Christian, when you're doing negative work on an object, it means that the object is losing energy. Put your pencil down, look up. So, potential energy, let's try that again, Hannah. Potential energy is stored energy. My mom says I have potential. Something different, Cole. Potential energy is stored energy. And there are different ways to store energy. There are many types of potential energy. A classic one is a bow and arrow. When you pull on a bow, you're exerting a force. When you stretch it, you're stretching it over a distance. There is a force, there is a distance. You have done work, which means you have added energy to the system. You have stored energy in the bow. Suppose it takes 250 newtons of force to pull the arrow back 0.78 meters. How many joules of energy are stored in the bow? Well, energy, which is the ability to do work, can be calculated using the work equation. Sierra, how many newtons of force? Now, I should point out that's an average force. Anybody here shot a compound bow or anything like that? The force is not constant. It's harder to pull it first and it gets easier. And so you're going to notice often in the homework, or if I give you this question in the future, I like this question, I like this question, I like this question, I'll probably say average force just to hedge my bet because I know it's changing. So this is an average force. Sierra, what was it? And how much distance did we pull it back? How many joules of energy are now stored in the bow? How much work did we do?
195.
Even? 195 units, Tristan? Joules. Where'd that energy come from? The sugar that I ate in the morning? The chemical energy in the food that I ate? When I release the string, what happens to that stored energy? It gets transferred. What does it get transferred to? Yeah. It turns into kinetic. Put in brackets the arrow. Put your pencil down. Next page. So when you stretch a rubber band, you are storing potential energy. A battery has stored potential energy in the form of electrical energy. But in this unit, we're going to be looking at one specific type of potential energy the most. So potential energy is stored energy, but we're going to be looking at gravitational potential energy. This is the energy you give an object when you lift it up. The fancy definition, Cole. This is the work you must do against gravity in order to change an object's height. I wonder what the equation for this would be. Let's see if we can figure it out. So, you agree with me, the amount of potential energy that we store in gravity, look up. If you just see potential energy, it's probably going to be gravitational potential energy, unless it's the bow and arrow question. Hint, 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 hint. What did you say it depended on? mgh. Mr. Dewick, isn't that the amount of work to go up the stairs? Yeah, because what you were doing was you were changing your own height, and that you were then gaining potential energy and losing food energy. So, potential energy is going to be mgh, or if you know the weight in newtons, potential energy would be the force of gravity times height, because the force of gravity, get the obvious one, was mg. This starts to explain why you can jump higher on other planets with less gravity. Jaden has a mass of 75 kilograms. First of all, review. 12 classes left. That's it. I counted. 12. We're almost to single digits, so I'm trying to work in as much review as I can. What does Part A want me to find, Maggie? No, now. What does Part A want me to find? No, now. I'm also going to work in as many bad jokes as I only got 12 more days! What was weight? Was that the same as mass? Okay, so not the same as mass, because mass is measured in kilograms, but mg is measured in newtons. So when I say weight, I'm giving you a hint, a multiple choice question that might show up on your final exam. You should know the difference between weight and mass. I want you to find mg, which is going to be 75. Oliver, what was g? Yep. I think you were the one that told me this in the last lesson too. 75 times 10 is 750, so it's going to be 750 minus 50. Is it 735? Double check me. Yeah. Still can do math in my head. And that would be newtons. Okay. When Jaden jumps, he can raise his center of mass 75 centimeters from the ground. Cross out 75 centimeters. Nice try. I don't do physics with centimeters. What am I going to write there instead? 0.75 meters. At the top of his jump, how much potential energy does he possess? Now, a few days ago, Hannah, we said this was the work done in climbing or lifting, but now I'm saying the reason work was involved is there's an energy transformation going on here. The potential energy is going to be mgh, which is going to be 75 times 9.8 times 0.75. Or if you're really lazy, you could just go 735 times 0.75, because that's what that part works out to if you happen to have that on your calculator already. How much energy does he have at the top of his jump? Cole? 500? 551.15? Is that right, folks? 0.25? 551.25? Is that right? 0.125. You know what? I'm going to go like this. 551, and then there's a little bit left over, because going to 6 sig figs is probably too accurate. Oh, were we multiplying? How many sig figs does 0.75 have? 2. How many sig figs does 75 have? How many sig figs does 9.8 have? Just to review sig figs. So how many sig figs should I go to in my answer if I'm multiplying? If I have 2, if I have 2, if I have 2. So really 550, but we're not being fussy with sig figs, but I will ask you a couple of sig fig questions on your test, on your final. Did I say 12 days left? Holy smokes, Batman. Where did energy come from? Energy came from the food that he ate. Soccer players, good luck. Is this quarterfinals or semifinals? Nice. You guys playing out in the backfield? Yeah. I would totally come watch you. Our golfers are doing their tournament at Golden Eagle, but the rest of you go see the girls in the backfield after school. Hey, how much potential energy, how much gravitational potential energy does an object have if it's sitting on the ground? Cole, why? Yeah. That can be handy because when we're trying to calculate total energy, if you're on the ground, that gives you something you can just ignore. Kinetic energy. Kinetic energy is the energy of motion. Going to pause again. Kinetic energy, and I usually use KE for kinetic energy and PE for potential energy, is actually equal to 1/2 mv squared. Why squared? Because it is, and I can prove it to you next year. Why 1/2? Because it is, and I can prove it to you next year. But the fact that this is how much energy a moving object has, although you don't realize it, we can now explain a whole bunch of things involving riding bike and running that you might have wondered, or maybe if you weren't curious, you didn't wonder about, but now that I mention them, you're going to start to notice. This squared plays a huge role in your life. Magnum bullet weighs 8.1 grams. Cross out 8.1 grams. We don't do physics with grams. What is 8.1 grams in kilograms? Something to do with 1,000. Times or divide? By the way, 8.1 grams, is that a lot of mass or a small amount of mass? So I don't think it's times by 1,000 because that would give you 8,000 kilograms, which is several cars. So clearly it's divide by 1,000. So what is it? 2 zeros and then 8.1? Yes? Travels at 490 meters per second. The speed of sound is 330 meters per second. This bullet is supersonic. And this is about the speed of a Magnum bullet. I looked it up. How much kinetic energy does it possess? Well, kinetic energy is 1/2 mv squared. Both of these equations are on your green sheet. Yes, you do have potential energy equals mgh, and you do have Ke equals 1/2 mv squared. It's going to be, how do I type 1/2 on my calculator? Yeah, 0.5. You can also type 1 divided by 2, but 1 divided by 2 is 3 keystrokes. 0.5 is 2 keystrokes. Yes, I think that way, and I want to save time anywhere I can. 0.0081. 490. Most common mistake, kids write the squared, and they're so proud because they wrote the squared, they remembered the squared, they forget to type the squared. So don't forget that. What do you get? This I can't do in my head. There's a squared there. It's going to be big-ish, maybe? What'd you get, Mateo?
I think I got this right. It's 7.8764.
Anyone else? 7.7864?
Yeah, never mind.
Try again. What'd you get? 972. 972?
Yeah.
You know what? A bullet has almost 1,000 joules if you're looking for a rough. Okay, 972. If that bullet enters a target and comes to a stop, where'd that energy go? What's its kinetic energy if it comes to a stop? Goes into destroying the target. That energy does have to go somewhere. It can't just magically vanish. Okay? It's why if the bullet goes through the target and keeps going, it does less damage to the target itself, although in human beings there's exit wounds which are yucky, and I'm not going to go into the disgustingness of that, but if we're just talking about like a hay bale target or something like that. Example 5. A car has a mass of 1,000 kilograms. I'm about to explain something to you. If I do my job right, this might be a... Oh. Emily, what does A want me to find?
Kinetic energy.
More specific?
That's required to just be 1,000.
So it's going to be 0.5 times 1,000 times 5 squared. Yes? I think I can do this in my head. It's going to be 25 times 1,000 is 25,000. Half of 25,000. Is it 12,500? Okay. Emily, in part B, how fast are we going? Twice as fast? Does twice as fast take twice as much? Crunch the numbers and find out. So it would be 0.5 times 1,000 times 10 squared. I don't think you get twice as much, because twice as much would be 25,000. That's not what you get. You get 50,000? Could you go 50,000 divided by 12,500? How many times bigger is that answer than that? 4 times bigger. Twice as fast is 4 times bigger? Emily, how is this 15 related to that 5? 3 times faster? How many times more energy do you think 3 times faster is going to take? Let's find out. What do you get? Yep. I'm going from memory. I didn't do this in my head. 112,500? Do me a favor. Can you take this number, divide it by the original answer? How many times bigger is this?
9.
Yeah.
9.
Yeah. 9. Yeah. You'll miss that, Joe. Oh, 9 times larger? So, 2 times faster made 4 times, don't write this down, larger. 3 times faster made 9 times larger. Make a guess. What do you think 4 times faster would require? Are you spotting the pattern? 16. Huh? Emma, what's on the V right there? 5 times faster. What's 5 squared? What's 5 times 5? 25 times more energy. This is why, and as soon as you start driving your cars and paying for your own gas, you'll figure this out. This is why going faster hammers your gas mileage. Okay? The faster you go, it's not a linear relationship. It's not, oh, if I go twice as fast, I'll use twice the gas. You're going to use 4 times the gas, fella. Okay? That's how it works. Or, so let's look at example 6, next page. Suppose an object has 5,000 joules of kinetic energy. If I want to double its speed, how much more energy will I need? Emma, double is 2. What's 2 squared? Which is going to be 20,000 joules. Twice as fast, 4 times more energy. What if I want to triple its speed? Triple, what number is triple? 3 squared, Emma?
9.
Yeah.
No.
which I think is going to be 45,000 joules. If I wanted to quadruple its speed, it's going to be 16 times as much, which is going to be 5,000 times 16, 80,000? Double check me. Yeah? So the first thing I would say to you as you start to pay for your own gas is the difference between going, let's say, on the Trans-Canada or on the Coquihalla, doing 110 and doing 140, you're going to use way more gas going 140. It's going to hammer you in the bank account. And so you need to ask, is that extra 30 kilometers per hour getting there a little bit faster, is it worth it financially with gas prices right now? I'm going to say to you, probably better just to leave a little earlier. Just saying. This also explains why sports equipment like golf clubs and tennis rackets and hockey sticks, any sport where you strike another object, they become heavier. Sorry, they become lighter, not heavier, because in golf, for example, we talk about club head speed. You're trading off a bit with the mass because there is an M in the equation, but is there a squared on the M? Where is the squared on in the equation? It'll a little lighter to be able to go faster. You're going to get way more bang for your buck with that V squared. This also explains why it's more difficult to speed up once you've already possessed kinetic energy. Many of you have ridden your bike when you're a kid. I don't know if you've noticed, but to start from 0 and go medium fast, and then to go from medium fast to really fast, that second one takes way more energy. Even though there's not that big an increase in speed, it's because there's a squared on the equation. That energy's got to come from somewhere. Maggie, it's coming from the sugar that you eat. It's pretty easy to go from 0 to 5. It's tougher to go from 5 to 10 meters per second. It's even tougher to go from 10 to 15 meters per second, even though each one of those is a 5 meter per second increase. I'm telling you, next time you're riding your bike, just feel what's going on through your body. Get up to medium speed and then say, okay, I'm going to try and double my speed. It will not take twice the effort. It will take way more than that. And now I got to be a bit serious to all of you who are young, stupid drivers, and all of you are. This is why the damage done to occupants in car accidents is so dramatically different between an accident at 20 kilometers per hour and an accident at 80 kilometers per hour. How many times bigger, Mateo, is 80 than 20? They're going to have 16 times more damage to the occupants. Not 4 times more damage because of that squared, 16 times more damage. Oh, and since work is also still force times distance, if you're going 4 times faster, it's going to take you 16 times longer to stop, further to stop. And that's one that many drivers don't realize. They think, I'm going twice as fast, I'll need twice the stopping distance. No, you're going to need 4 times the stopping distance. Whatever you practiced before, it's not going to work the same. I just explained a lot of stupid accidents with that little bit of physics right there. Because a lot of accidents, I thought I could stop in time. Yeah, bad physics. Brian, what's example 7 want me to find?
Velocity.
I got to be fussy. I didn't say velocity. What word did I use here? Word being letter F? Fast. Cole, what did you whisper to yourself? Speed. I deliberately didn't say velocity. We're in Scalarville here. And I gave you, what's KE an abbreviation for? Let's write down that equation. Kinetic energy is equal to mv squared. Look up, look up, look up, look up, look up. What number was in front of the mv squared? No, that's not what I wrote. What did I write in front of the mv squared? I didn't say 0.5, Oliver. What did I say instead? I'm going to write that like that. Because isn't over 2 the same as 1/2 times? Now, why did I do that? What's this question asking me to find? Which variable is how fast? Here's yet another equation. How would I get the v by itself? What am I going to do with the m to move it over? Divide. What am I going to do with the 2 to move it over? That's why I wrote it that way. It's a little easier to see where that 2 is going to go. Oh, but that's going to give me this. So you're right. The KE stays where it is. You're telling me a 2 is going to go right there. You're correct. You're telling me an m is going to go right there. You're correct. But Brian, that's going to give me a v squared. Oh, we've done this before too. How to get rid of a squared. I did not put that equation on your formula sheet on purpose. I think you can derive it. So if we plug in numbers, it's going to be 2. The kinetic energy was 924.5. M is 25. How do we type these? Do you remember? I always suggested I type what's inside the square root first. 2 times 924.5 divided by 25 equals, and then I go square root, answer button. Some of you that have the newer calculators, I think Tristan's, for example, you might, when you hit the square root button, it might do a lovely little indentation and a little box, in which case you can just do it in one step, but mine doesn't. You get 8.6? Units, what did we just find, Bri? No? Yes? Units? What it's always been. No, we've never done speed in kilometers per hour. Darn right, meters per second. Okay? In other words, the kinetic energy equation actually has 3 variables. Kinetic energy, M, and V, as far as I'm concerned. As always, if I give you 2, you can find the third. This is also the physics of roller coasters. This is what you use to design roller coasters. A roller coaster has a kinetic energy of 137,200 joules at the bottom of the first hill. First of all, how fast is it traveling? Chloe, what's this question asked me to find? Speed. You know what? Let's just walk through that again. So it was mv squared over 2. I wrote it that way because I know I'm not getting the KE by itself. I'm getting something else by itself. By the way, there is an invisible 1 there if you really want the 1/2, but Emma, is a 1 going to make any kind of a difference at all? So you've had me long enough to know I tend to abbreviate. Am I going to write the 1 if I don't need to write the 1? I say. How would I get the V by itself, Chloe?
Multiply.
More specific. What's going to stay where it is, like a domino? KE. How am I going to move the M over?
Divide.
How am I going to move the 2 over?
Multiply.
And that's going to give me V squared. Knock, knock. How to get rid of squared?
3.
Okay. It's going to be 137,200 divided by 350. What do you get? How fast are we going? This is some of what my students tomorrow in Physics 12 will be analyzing. We'll be analyzing roller coaster. If you take Physics 12 next year, you'll be doing the same thing. This gives you an idea of how we can figure out speeds. What'd you get? 28 even? Is that fast? How do I go to kilometers per hour? It had something to do with the 3.6. Okay, times it by... how fast is that in kilometers per hour? Times by 3.6, what do you get?
176.4.
How fast?
176.
It can't be 176.4.
100.8.
108.
100.8.
100.8. That's not bad. 100 kilometers per hour, that's freeway speed on a roller coaster. That's a B+ ride. Maybe even an A-. I've been faster, but there's not that many that go much faster than that. Is your calculator working okay here today?
I don't know. 28 times 6.3?
No, 3.6.
3.6. There we go.
Wow. Let's suppose you're a ride designer, Tristan, and at the bottom of that first hill, that's how fast you want them to go. Where does that energy, that kinetic energy, come from? It comes from the potential energy of the first hill. How high does that first hill have to be? Ooh, now we can talk about ride design. Potential energy. What was my equation for gravitational potential energy? It's on your green sheet if you've forgotten. Oh, MGH? Tristan, what's this question want me to get by itself when it says how high? Oh, what are the M and the G doing to the H? Adding, subtracting, multiplying, or dividing? How will I move them over? So you're telling me the height of the first hill is going to be the potential energy divided by mg. M was 350. G, Oliver? Good. Potential energy. Oh, all of the kinetic energy. Tristan, how much kinetic energy was there in the original question? No, that's speed. How much kinetic energy was there in the original question? Yeah. And believe it or not, this is how they do it. This is how you figure out how high that first hill has to be. Oh, sorry. In real life, you'd lose a tiny bit to friction and sound, and you would have to take that into account. But you'd start with this, and then you'd adjust it. What do you get? 40 even?
Yeah.
Really? Wow, I made up nice numbers. I normally don't do that. And height is meters, yes? Okay. How high would we need to lift a 65 kilogram object to give it a potential energy of 15,288? This is the same question we just did. Yes? We would start out by saying, well, potential energy is mgh. Tristan, how would I get the h by itself? More specific. Divided by what? Yeah. So you can see it's the same as part B. Different numbers is all. So it's going to be 15,288 divided by 65 times 9.8. Which is what? Oh, is this a fraction? Yes. Is there more than one thing on the top? Is there more than one thing on the bottom? Oh, good review for making sure we type things into our calculator correctly, not that I'm mentioning any names. What do you get? Wow, I took the time to make these work out evenly for you? I don't remember doing that or caring enough of them. Okay. And height would be meters, right, Maggie? Okay. What else can we do with this now? Turn the page. This is the physics of pile drivers. Not the wrestling move, the actual thing that pounds poles into the ground. So suppose we want a 2,500 kilogram pile driver to hit the ground at 18 meters per second. First of all, how much kinetic energy does it need? Ke equals a half mv squared, or mv squared over 2. Did they give me the mass? Did they give me v? Oh, this is straight plug and chug. A half m 18 squared. How much kinetic energy do we need if we want it to hit the ground at 18 meters per second to pound the pole into the ground? What'd you get? Sorry? 405 and 3 zeros? Units, this is energy, joules. So, if you're the engineer and this is the pile driver, and I'm guessing they just pre-programmed this and let the computer take care of it, what's the height you need to tell the computer to raise the pile driver for? What does this want me to find? Dylan, what does this want me to find? Can you look at the potential energy equation without writing it down? And can you get the h by itself in your head, please, and just give me my new equation for height? I don't see joules. That's not in the equation. It doesn't say joules equals mgh. I think it says something else equals mgh. Isn't it PE divided by mg? Because isn't the equation PE equals mgh? And you... Yes? Okay. That's what I was getting at, right? Rewrite the equation. How many joules of energy? Well, how much kinetic energy do we need, Dylan? So how much potential do we need up there? Same answer. Wow. Did they give me the mass? Did they give me G? I know G. How high do we need to lift this pile driver before we let it drop? Sorry? 16.5? Okay, and if you were in a situation where there was like a tree overhead or something and you couldn't do that, you had luck. No, you have to get a heavier pile driver. You need to change the mass. That's your workaround. 16.5, is that agreed?
Yep.
Speaking of getting a heavier mass, What's 11 asking me to find? Mass. Given what? Given what piece of information? Okay, by the way, the reason we're doing that now is we're almost done the year. We have a bunch of equations with mass in them. There's F equals ma, there's P equals mv, there's a half mv squared, there's mg. So now we got to just say, okay, what do they give me? Which equation am I going to write down? I see kinetic energy. I'm starting here. Except, Christian, usually when I'm rewriting the equation, instead of writing a 1/2, I just tuck a 2 down there because that's cleaner. What are we trying to get by itself now? How? What do I do with the v squared? Divided. What do I do with the 2? So here's yet another equation. Please don't memorize these. We can derive these. You're telling me that the KE would stay where it was. We would times the 2 over and divide by the v squared. You might also be able to use that, for example, to figure out the maximum mass of the roller coaster cars that you were designing for your ride. Say. It's going to be 2/1764 divided by 7 squared, which is what? Even? Wow. Units for mass, Christian. So, as any new concept, in the potential energy equation, MGH, there's potential energy, there's M, and there's H. G is 9.8, so that's not really a variable. If I give you any 2, you can find the 3, and same with the kinetic energy equation. If I give you any 2, you can find out the third. Okay. I'm going to give you your homework, and then I got a short video to show you as well. So number 1 is good. 2 is good. I'm probably going to assign most of these. 3 is good. 4 is good. 5 is good. 6 is good. 7 is good. Yep. 8. 9. You know what? You'll cross out 9. We'll skip 9. We'll say 9. 9. Nothing? Okay. 10 is good, though. 11. What's the potential energy of a 3-kilogram ball that's on the ground? Cole, what's the answer to number 12? If it's on the ground, how much potential energy do you have? Oh, you already all did number 12, so you can skip number 12. But if you're on the ground, 0. Skip 13, 14, 15. 17. I skipped 16. It's a lot, I know, but you'll get really good at this. We've been talking about energy transformations. I've been arguing you could give an object potential energy, stored energy, and then if you let it go, it'll turn into kinetic energy. And we're going to be talking about that even more for the next few days. There is a commercial that came out about 10 years ago. Honda made it. It's called COG. It won an award that year for being the best commercial of the year. What they did is they took apart a Honda and they made a massive chain reaction machine. See if you can spot the energy transformations